All right, today we're going on a hunt. But not for just any ghost. We're looking for the most elusive, mysterious, and, believe it or not, abundant particle in the entire universe. So let's begin the search for the neutrino.
Okay, look at this number on your screen, 100 trillion. I mean, that's a number so big it's hard to even wrap your head around it. So what do you think it is?
Well, that is the number of invisible particles, neutrinos, that are passing right through your body every single second. They come from the sun, they stream through you, and you don't feel a thing. Kind of mind-bending, right?
So what is this invisible presence? This is the neutrino, often called the universe's ghost particle, and it's one of the most fundamental and strangest building blocks of our reality.
You know, what's funny about the neutrino is you can almost define it by what it isn't. It has no electric charge. Its mass is so tiny it's almost nothing, at least 10,000 times less than an electron. And its most famous trait? It barely interacts with, well, anything.
And that's exactly why we call it the ghost particle. It just ignores the everyday forces of nature. The strong force that holds atoms together doesn't feel it. Electromagnetism? Nope. Matter is basically transparent to it. To put this in perspective, and this is just wild, a single neutrino could fly through a light year of solid lead and probably not even notice. That's how little it cares about the rest of the universe.
Okay, so if these things are practically impossible to catch, how in the world did we figure out they even existed? Well, that's where the story gets really good. It's basically a scientific detective story that took decades to unfold.
The whole puzzle started at a sort of cosmic crime scene, beta decay. Physicists were watching this process where a neutron decays into a proton and an electron, and they noticed something was off. The numbers didn't add up. Energy was missing. It just seemed to vanish. And that was a huge problem, because the conservation of energy isn't just a suggestion, it's like rule number one of physics.
So along comes Wolfgang Pauli in 1930 with what he himself called a desperate remedy. He basically said, what if there's a tiny invisible thief, a new particle that's carrying away the missing energy? Then in 1934, the great Enrico Fermi gave this particle a name, neutrino, which is Italian for little neutral one. But it was one thing to name it, and another to find it. It took all the way until 1956 for Rains and Cowan to finally detect one, in an experiment they perfectly named Project Poltergeist.
And you have to understand just how radical this idea was. Pauli himself was deeply worried. He actually wrote, "I have done something very bad today by proposing a particle that cannot be detected." He thought it was, bad science to just invent something you could never prove. Turns out, he was right. And also wrong. It was detectable, just incredibly, incredibly hard to find.
But you know how it goes in science. You solve one mystery and a bigger one pops up. Once we could finally detect these things, we point our detectors at the sun, which should be a massive neutrino factory. And we hit another wall. We were only detecting about 1/3 of the neutrinos that our theories predicted. So what was going on? Was our understanding of the sun completely wrong? Or was something bizarre happening to these particles during their 8-minute trip to Earth?
Well, the answer, it turns out, was way stranger than anyone imagined. The neutrinos weren't missing at all. They were hiding. They were changing their identity, like a quantum shapeshifter.
Okay, to get this, you need to know that neutrinos come in 3 types, or flavors. There's the electron neutrino, the muon neutrino, and the tau neutrino. Now, here's the key. A neutrino is always born as one flavor, and it's always detected as one flavor. And those early solar experiments, they were only designed to see one kind, the electron neutrino.
But, and here's the quantum weirdness. When a neutrino is traveling through space, it's not in a pure flavor state. Instead, it's a mix, a superposition of 3 different mass states. You can think of the mass states as the true underlying identities of the neutrino, the things that actually have a specific mass.
So let's break that down. The flavor, like electron neutrino, is how the particle interacts with the world. The mass states are how it travels. The absolutely crucial point is that a single flavor is really a quantum mixture of the 3 mass states. It's like a cocktail recipe. An electron neutrino isn't one thing. It's a specific mix of mass state 1, mass state 2, and mass state 3.
And this is how the magic happens. This is oscillation. A neutrino is born, say, as a pure electron neutrino. But as it zooms through space, those 3 mass components that make it up, they actually travel at slightly different speeds. So their quantum waves get out of sync with each other.
And as they go out of sync, the recipe for the flavor changes. So by the time that neutrino from the sun gets to Earth, it might have morphed into a muon or tau neutrino. The missing neutrinos weren't missing, they had just changed their disguise.
And this discovery, this was a bombshell. It was absolutely revolutionary. Why? Because for this whole oscillation thing to work, the mass states have to have slightly different masses. And that meant neutrinos must have mass. But the standard model of particle physics, our best theory of everything for decades, insisted that they were massless. This was the first major crack in the standard model, the first piece of hard evidence that our beautiful theory was wrong, or at least incomplete.
But you see, a crack in a theory isn't a bad thing. It's an opportunity. It's where the new physics lives. And this particular crack opened the door to something much, much bigger. What if this tiny, elusive ghost particle holds the answer to maybe the most profound question we can ask?
And that question is, why does anything exist at all? I mean, really think about that. Why are we here? Why are the stars here? Why is there a universe filled with stuff instead of just nothing?
Okay, so our best understanding of the Big Bang says that it should have created matter and antimatter in perfectly equal amounts. And whenever matter meets its antimatter twin, poof, they annihilate each other in a flash of energy. So, logically, the universe should be an empty, boring void of leftover energy. But obviously, it's not. We're here. Somehow, for every billion matter-antimatter pairs that destroyed each other, just one single matter particle was left over. And that tiny 1 in a billion surplus, that's us. That's everything.
So how did that happen? Well, the neutrino might be our prime suspect. For matter to win out, there had to be some fundamental difference in the rules for matter versus antimatter. This is something physicists call CP violation. And guess what? Recent experiments, like T2K in Japan, are seeing these really tantalizing hints that neutrinos and their antimatter counterparts, antineutrinos, don't play by the exact same rules. They seem to oscillate just a little bit differently. And that tiny asymmetry, that could be the reason we exist.
And if that's not weird enough for you, there's an even wilder idea out there. What if the neutrino is something called a Maggiora particle? This would mean it is its own antiparticle. It would be both matter and antimatter at the same time. No other fundamental matter particle is like that. And if it's true, it would open up a whole new playbook for physicists to explain exactly how matter won the cosmic war in the first seconds of the universe. So, that brings us right up to the present day. And honestly, the hunt for the neutrino's deepest secrets is one of the absolute hottest, most exciting frontiers in all of physics right now. And this is basically the treasure map for the future of physics. All around the world, teams are building these enormous, incredible experiments to chase down the answers. They're trying to nail down the exact mass of the neutrino. They're trying to see for sure if there's CP violation, that difference in how neutrinos and antineutrinos behave. And of course, the big one. Are they Majorana particles? Each of these questions is a doorway to a deeper understanding of reality itself.
So just think about this journey. We started with a desperate remedy, just a little fudge factor to save a law of physics. That little remedy grew into a particle that broke our most cherished theory, the standard model. And now it might just hold the ultimate answer to why we or anything exists at all. The ghost particle has been whispering the universe's secrets to us for nearly 100 years. And the most exciting part? We're only just now, finally, learning how to listen.